In this lecture, we are going to talk about utility functions. In our previous chapter on preferences, we defined certain terms like completeness, reflexiveness, transitiveness, and continuity. Now we say that a preference relation that satisfies all these properties, completeness, reflexiveness, transitiveness, and continuity, can be represented by a continuous utility function. We say that a utility function represents a preference relation if and only if the following properties are satisfied. First, if there are two bundles, say x0 and x1, then if a consumer strictly prefers bundle x0 to bundle x1, then the utility that the consumer derives from bundle x0 is strictly greater than the utility that the consumer derives from bundle x1. Second, if there are two bundles x0 and x1, and if the consumer strictly prefers bundle x1 over bundle x0, then the utility that the consumer gets from bundle x0 is strictly less than the utility that the consumer gets from bundle x1. And we say that if there are two bundles x0 and x1, and if the consumer is indifferent between the two bundles, then the utility that the consumer gets from these two bundles will be the same. Because when there are two bundles and the consumer is indifferent between them, it clearly means that both these bundles will lie on the same indifference curves, and all points on the same indifference curve corresponds to the same levels of utility. Now we are going to talk about two types of utility. First is the ordinal approach to utility, and second is the cardinal measure of utility. Now first, looking at the ordinal measure of utility, it is basically concerned with the ranking of the bundles. So suppose there are two bundles x and y. The utility that the consumer gets from bundle x is 4 and that from y is 1. Then we say that since ux is strictly greater than uy, therefore bundle x is strictly preferred to bundle y. However, we do not say that bundle x is 4 times better than y. We can say that ux is equal to 6, uy equals 4. It won't make a difference because it will still mean the same, that ux is greater than uy and hence x is strictly preferred to y. So basically what we are concerned with is the ranking of the bundles, the order in which the bundles are ranked by the consumer. Now let us take another example to clarify this. Suppose there are three bundles, 5, 1, 2, 3 and 3, 2. The consumer is indifferent between the two bundles 5, 1 and 3, 2, and the consumer prefers both these bundles over, strictly prefers over to bundle 2, 3, as you can see here. Now let us assign some numbers to each of these bundles. So the utility that the consumer gets from the bundles 5, 1 and 3, 2 is 17, and the utility that the consumer gets from the bundle 2, 3 is 10. So as u of 5, 1 and u of 3, 2 is strictly greater than u of 2, 3, we say that these two bundles are strictly preferred to the bundle 2, 3. But we might as well say that u 2, 3 is equal to 55 and the utility from 5, 1 and 3, 2 is 82. It won't make a difference because it will still mean the same, that the consumer is indifferent between the two bundles 5, 1 and 3, 2, and the consumer prefers both these bundles over the bundle 2, 3. So the ordinal approach to utility says that we are mainly concerned with the preference order of the bundles. The preference order should remain the same. The values that we assign, the numbers that we assign to each of the bundle can change, but then it should not affect the preference order of the bundles. Now talking about the cardinal utility, if one bundle is preferred to other, then we ask ourselves by how much? So when we talk about things like there are two bundles A and B and A is 3 times better than bundle B, then what we are doing is we are talking about cardinal measure of utility, where we cannot assign random numbers to the utility because of the cardinal measure that is attached with the utility. Now what we are going to talk about is the utility functions of special cases like Cobb-Douglas preferences, perfect substitutes, complements, max utility function and quasi-linear preferences, and then we will move on to look into marginal utilities, monotonic transformations and MRS. First looking into Cobb-Douglas preferences. Now Cobb-Douglas utility function can be represented in a general form as shown here. So u of x1, x2 dot 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 xn is equal to capital A x1 to the power alpha 1, x2 to the power alpha 2 dot 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 xn to the power alpha n. Here capital A is a constant, x1, x2 till xn, these are n goods, this is the quantity demanded of n goods, and alpha 1, alpha 2, alpha n, all of these are constants. Now in two good case, it will reduce to u x1 x2 equals a x1 to the power a, x2 to the power b, where again x1 and x2 are the quantity demanded of the two goods and capital A is a constant, and a and b are also constants. Now let's look into the graphical representation of the Cobb-Douglas utility function. So what we are going to do is we are going to draw the indifference map. Now suppose A is equal to B. When A is equal to B, then the indifference curves in case of Cobb-Douglas utility function will be symmetrical about the line y equals x. So as you can see in the left panel, when we have drawn the line y equals x, the indifference map looks symmetrical about this line. However, when A is less than B, then the indifference curves will be a little flatter, and when A is greater than B, then indifference curves will be a little steeper. As you can see in the right panel, for A less than B, A is equal to 0.2, which is less than B, 0.8, and therefore the indifference curves, they are flatter, and we say that in this case the indifference map won't be symmetrical about the line y equals x. Now we will look into the case of perfect complements. So we'll talk about yontiff utility functions. The general form of a yontiff utility function is u of x1, x2 dot 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 xn is minimum of alpha 1 x1, alpha 2 x2, alpha n xn. In a two good case, it reduces to u x1, x2 equals minimum of a x1, b x2, where x1 and x2 are the quantity demanded of the two goods, and it's basically a minimum function. Now what are a and b here? 1 by a is the quantity of good 1, that is quantity of x1, that is needed to get 1 unit of utility, and 1 by b is the quantity of x2 needed to get 1 unit of utility. So if x1 and x2 are coffee and sugar, and a consumer needs 2 spoons of sugar for 1 cup of coffee, so in order to derive 1 unit of utility, we say that 1 cup of coffee will give the consumer 1 unit of utility. So how many spoons of sugar we require? 2. So what will be 1 by B? In this case we have taken good 2 to be sugar. So 1 by B in this case will be 2. And similarly 1 by A in this case will be 1, because we need 1 cup of coffee to get 1 unit of utility. So substituting these values in the equation, ux1 comma x2 equals minimum ax1 comma bx2, will get the utility function as shown here. Since 1 by a equals 1, therefore a is also equal to 1, and since 1 by b equals 2, therefore b is equal to half. So we should be very careful while we are writing the utility functions. For in case of yontiff utility function, we should be very careful with the coefficients that we attach to x1 and x2. Moving on to linear utility function, that is the case of perfect substitutes. The general form is given by utility x1 x2 dot 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 xn is equal to alpha 1 x1 plus alpha 2 x2 plus dot 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 plus alpha n xn. So for n goods, it can be given, the utility can be given as summation of alpha I xi, where I is moving from 1 to n. Now in two good case, the utility function reduces to ax1 plus bx2. Again, it is very essential to pay close attention to the coefficients a and b that are being attached before x1 and x2. What it means is that the consumer is willing to substitute 1 by a units of x1 with 1 by b units of x2. So suppose we have two goods, butter and margarine, and the consumer is willing to substitute 1 spoon of butter with 1.5 spoons of margarine, then 1 by a will be equal to 1 and 1 by b will be equal to 1.5, which is 3 by 2. So a is 1 and b is 2 by 3. So a is 1 and b is 2 by 3. Therefore, the utility function becomes u x1 comma x2 is equal to x1 plus 2 by 3 times x2. Now it is essential to pay close attention to the coefficients a and b, because if a and b are wrongly written, then the slope of the indifference curve changes. That is, MRS changes, and that is why it is very essential that we correctly determine the values of A and B so that we get the correct utility function. Now we will talk about the max utility function, which is very similar to that of the minimum utility function. So instead of the minimum, we take the maximum of alpha 1 x1, alpha 2 x2 dot 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 alpha n xn. In a two good case, it is given by max alpha or ax1 bx2. Again, 1 by a is the quantity of x1 needed to get 1 unit of utility, and 1 by b is the quantity of x2 needed to get 1 unit of utility. So let us take an example. We have x1 and x2. x1 is the marks in eco test 1 and x2 is the marks in test 2. Now if 1 mark in eco test 1 is equivalent to 2 marks in eco test 2, you can say that test 1 was tougher as compared to test 2. Therefore, if you get 1 mark in test 1, that is equivalent to 2 marks in getting in test 2. Therefore, if the teacher says that the maximum of the two tests will be taken, then here 1 by a will be equal to 1, because 1 mark in eco test 1 gives 1 unit of utility, and 2 marks in eco test 2 gives 1 unit of utility. Therefore 1 by b will be equal to 2. Therefore our utility function becomes ux1 comma x2 is equal to maximum of x1 comma x2 by 2. Now looking into how the indifference curves will look in case of max utility function, we know that in case of yontiff utility function, that is min utility function, we have L-shaped indifference curves. Whereas in case of max utility function, the indifference curves are inverted L-shaped. So these are the indifference curves. They are inverted L-shaped, as you can see in the diagram, and this is the indifference map. Now let's talk about the last case, the case of quasilinear preferences. Now in case of quasilinear preferences, again the general form of the utility function is given by utility x1 comma x2 comma dot 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 xn is equal to vx1 plus x2 plus dot 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 plus xn. Now let's look into the two good case. It's vx1 plus x2. Now the thing in quasilinear utility functions are that it will be linear in one of the goods and it will be non-linear in the other good. So in this example, ux1 comma x2 is equal to vx1 plus x2. The utility function is linear in good 2 and it is non-linear in good 1. When the utility function is linear in good 2 and non-linear in good 1, we say that the indifference curves, they are vertical shifts of each other. So if we draw the indifference curves, they are vertical shifts of each other. So if this is one indifference curve, this will be the second indifference curve, this will be the third indifference curve, and the indifference curves, they will be vertical shifts of each other. Whereas if the utility function is linear in good 1 and non-linear in good 2, then the indifference curves, they will be horizontal shifts of each other. I repeat, if the utility function is linear in good 2, then they are vertical shifts, and if the utility function is linear in good 1, then the indifference curves are horizontal shifts of each other. Now we say that Vx1 in this case is a concave function. The question is why. Now a little later we'll talk about what MRS is. It's basically U1 by U2, which is equal to V dash x1 in this case. Basically it's marginal utility of good 1 divided by marginal utility of good 2. Now in this case the marginal utility of good 1 is V dash x1, marginal utility of good 2 is 1. Therefore MRS is equal to V dash x1. Now V dash x1 has to be a decreasing function because the diminishing marginal rate of substitution that we make as an assumption. Now since V dash x1 is a decreasing function, therefore the derivative of V dash x1 will be less than 0. The derivative of V dash x1 is V double dash x1. So the derivative of V dash x1 is V double dash x1 and it is less than 0. So we see that for the function Vx1, the first derivative is greater than 0 and the second derivative is less than 0. Therefore, clearly the function Vx1 is a concave function. I would request the students, those who don't know what are concave functions, to go back to the mathematical method of economics books to look into the conditions that need to be satisfied for a function to be concave. Now we will move ahead and we'll talk about marginal utilities. Now marginal utility basically means incremental. The word marginal means incremental. So we say that marginal utility of good I is the rate of change of total utility as the quantity of good I consumed changes by 1 unit. So the definition says marginal utility is equal to the change in the rate of change of total utility when the quantity of the good consumed changes by 1 unit. So mu is equal to del u by del xi. For example, if the utility function is x1 comma x2, then what will be the marginal utility for good 1? It will be delta u by delta x1. What will be the marginal utility of good 2? It will be delta u by delta x2, because it will be the rate of the change of the total utility as the quantity of the good consumed changes by 1 unit. Now this implies this. So mu1 is equal to delta u by delta x1 implies delta u is equal to mu1 into delta x1. It is nothing but just rearranging the terms on the two sides of the equation. Similarly, delta u is equal to mu2 into delta x2. So what is the total change in the utility? The total change in the utility will be the sum of these two. So the total change in the utility is mu1 delta x1 plus mu2 delta x2. Now we know that along a particular indifference curve the utility level remains the same. So the change in the utility is 0. Therefore this equation is going to hold, where mu1 delta x1 plus mu2 delta x2, which is the total change in the utility, will be equal to 0. Now just rearranging the terms on both sides of the equation, we get delta x2 by delta x1 is equal to minus of mu1 by mu2. So we get this equation, and this is essentially MRS, which is the marginal rate of substitution. Now let's move ahead to look into one example to clarify our concepts of marginal utility and MRS. So let us take a utility function as given here, which is equal to x1 to the power half x2 to the power 2. It's basically a Cobb-Douglas utility function. So this is a Cobb-Douglas utility function. Now for finding the marginal utility of good 1, we will take delta u by delta x1. So we will do partial differentiation of this utility function with respect to x1. And for finding the marginal utility of good 2, we will do the partial differentiation of the total utility function with respect to x2. And we will get the following values. For MRS, we will simply do minus of mu1 divided by mu2, and we will get x2 minus of x2 divided by 4x1. So we will get minus of x2 divided by 4x1. Now let's talk about monotonic transformation. A monotonic transformation of a utility function is a utility function that represents the same preferences as the original utility function. So the preference or the ranking of the bundle won't change when we take the monotonic transformation. Now when I'll be talking about monotonic transformation, what I'll mean is positive monotonic transformation. Because if we take negative monotonic transformation, then the results that we will be getting will be just the opposite of what is desired. Now let us take an example. So if we have a number, say u, and we have a function f of u, which is a monotonic transformation of this number u. Then if u1 is strictly preferred to u2, then we will imply that f of u1 is also strictly greater than f of u2. So what we say is that the preference order or the ranking of the bundles does not change when we take a monotonic transformation of the number u. The order of the preference is preserved. Now if we have to calculate the rate of change of the function f of u as u changes, we can do so by using this formula, which is f of u2 minus f of u1 divided by u2 minus u1. Now let's look into monotonic transformation mathematically. So as you can see, suppose there are two bundles, x1 comma x2 is one bundle and y1 comma y2 is another bundle. Now if the consumer strictly prefers the bundle x1 comma x2 to y1 comma y2, then we will say that u of x1 comma x2 will be greater than u of y1 comma y2. We talked about this in the beginning of this lecture. Also, if the utility that the consumer gets from the bundle x1 comma x2 is greater than the utility that the consumer gets from the bundle y1 comma y2, then we will say that f of u of x1 comma x2 is also greater than f of u of y1 comma y2. Now this will be true if the function f is a monotonic transformation of u. From these two equations, equation 1 and equation 2, we can conclude equation 3, which says that if the consumer strictly prefers bundle x1 comma x2 to bundle y1 comma y2, then the consumer prefers f of u x1 comma x2 to f of u y1 comma y2. It can be given by this equation. So we have proved that the monotonic transformation is going to preserve the order of the preferences. So if one bundle is preferred to the other, the utility that the consumer gets from the first bundle will be greater than the utility that the consumer gets from the second bundle. However, when we take a monotonic transformation, then f of the first bundle will be greater than the f of the second bundle, which means that when we have taken a monotonic transformation, the order of the preference has not changed, it has been preserved. Examples of monotonic transformation are if we multiply by a positive number, or we add any number, or we raise u to an odd power, not an even power, odd power, then we will be getting monotonic transformations. So here is a task for you guys. Are the following monotonic transformations? I'll briefly discuss them. The first one is 6v minus 4. So if v is the utility function, then 6v will be a monotonic transformation because it has been multiplied by a positive number. I'm talking about this example. And if we add minus 4 to 6v, then we will get 6v minus 4. So essentially this is a monotonic transformation. 6v minus 4 is a monotonic transformation because it involves multiplication by a positive number and it involves addition of any number. In this case, minus 4 is being added. Talking about, let us take the case of log v first. Yes, this is again a monotonic transformation. Let's take another case. Okay, I'll just draw the graph for log v. So it is this. And from graph it is very clear that it is a monotonic transformation. Now let's take the case of u is equal to v square where the utility function is raised to an even power. So the graph of u equals v square looks something like this. And as you can see, this is not a monotonic transformation. This is not an increasing function. For monotonic transformation, the function should be increasing. In this case, when we took log, it was an increasing function, but this is not an increasing function. Either it should be an increasing function or it should be a decreasing function. But it should not be decreasing and then increasing. If it is a decreasing function, then it will be a negative monotonic transformation. Now if we talk about this case, u is equal to v square for v equal to 0. So we are just talking about the points where v is greater than 0, so this point. So we see that for this it is an increasing function, so this represents a monotonic transformation. So u is equal to v square is not a monotonic transformation, but u equals v square for v greater than 0 is a monotonic transformation. If you look at u equals v square for v less than 0, it will be this. The graph will look something like this. So it's a negative monotonic transformation. And if we look at the last case, u is equal to 1 divided by v square, then this is equal to v to the power minus 2. And as a result, it is not a monotonic transformation. Now, last thing that we will be discussing in this chapter is a question. And the question is, Applying a monotonic transformation to the utility function representing a preference relation simply creates another utility function that represents the same preference relation that we have defined. It's basically the definition of the monotonic transformation. Now the question is, what happens to the marginal rate of substitution? What happens to MRS when a monotonic transformation is applied? And the answer is there is no change. Let's look into how. Now first we will take an example. So we have a utility function, a Cobb-Douglas utility function, x1, x2. So ux1, x2 is equal to x1 multiplied by x2. What will be the MRS in this case? MRS in this case will be minus of mu1 divided by mu2. In this case, what is the marginal utility of good 1? It is x2. What is the marginal utility of good 2? It is x1. Therefore, MRS is minus of x2 divided by x1. Now we are going to take a monotonic transformation, v is equal to u square. So we have a monotonic transformation here, vx1 comma x2 is equal to x1 square x2 square. Now we have to find MRS in this case, and we will try to find if the MRS remains the same. So MRS in this case will be minus of del v by del x1, that is the marginal utility of this of the utility function v with respect to x1 divided by marginal utility of the utility function v with respect to x2. And when we calculate this, we get minus x2 by x1, which is the same as what we obtained when the utility function was x1 comma x2. So we clearly see through this example that when a monotonic transformation is taken, the MRS does not change. However, this does not lead us to the conclusion that this will always happen. This has happened for a particular example. So for this to always happen, we will take a general case and we will prove it so. So if we take a general case where v is equal to f of u is a monotonic transformation, f is a strictly increasing function, because that needs to be true for a monotonic transformation, then we see that MRS is equal to minus del v by del x1 divided by del v by del x2, which was essentially what we wrote here. This is equal to minus f dash u multiplied by del u by del x1. So what we are doing is, first we are doing partial differentiation of the function v, which is a monotonic transformation, with respect to x1, and then we are doing it with respect to x2. So we get this, and from that we will get the following equation, which is equal to minus of mu1 divided by mu2, which is equal to the MRS. Therefore, we conclude that MRS is the same in both the cases when we take monotonic transformation and we do not take monotonic transformation. Therefore, we get a very important result that MRS remains the same. MRS does not change when a monotonic transformation is applied.